Hello everybody, thank you for joining me in a recording today. You may have reached this video from clicking on through the notes that I've given you in the handouts about why Edexcel or any exam board for the A-level maths course in the UK, why don't they do integration from first principles? Why isn't that on the specification? You have to learn about differentiation from first principles in different contexts, for example differentiating sine and cosine from first principles, so why not integration from first principles? So essentially, the very short answer is because it's very, very hard indeed. And what I'm going to do here is to show you just how hard and tricky and horrible looking it is, just by proving from first principles how you might want to show robustly that the integral of x cubed dx in between, say, a and b is one and the same as the exact area under the curve of that graph in between the limits of x equals a, x equals b, the x-axis, and y equals f of x. So let's have a look at how I would probably imagine if it were on the syllabus it would look in a question. First of all though, we're going to need some results. So what we need to know are certain power sums. So if you do further maths as well as standard A-level maths, this would really help. But anyhow, I'll just quickly explain what I mean by power sums. The first one, if I'm adding up units, unit plus unit, adding up ones from k being equal to 1 from k being n. K is a dummy variable. All it means is that k can take any value from 1 to n. So all this means is if I sum 1 n times, because k goes from 1, 2, 3, 4, all the way up to n, the sum of n units is of course n. The next power sum we need is a fairly famous one, the sum of the first n natural numbers. So when k is 1, k is 2, k is 3. So, for example, if n were 4, that would be the sum of the first 4 natural numbers, 1 plus 2 plus 3 plus 4. This is a famous result which Gauss proved according to a very famous anecdote. Well, not proved, but realised when he was only a child. That's also written as half n brackets n plus 1, because this could be factorised further. Another result we need is the sum of the first n square numbers. So this result here, the first n square numbers is 1/6 brackets 2n cubed plus 3n squared plus n, and finally we're going to use the sum of the first n cubed numbers, which is actually 1/4, then in brackets n to the power 4 plus 2n cubed plus 4n squared. If you want to see where these results themselves come from, you can actually prove these by using systems of simultaneous equations. But I'm not going to go into that in too much depth, but I will show you on a hyperlink how this result could be proven for some of the first n squared numbers. I proved this result in a video before for year 12, talking about this in a similar way, but in not quite as much depth. So I'll put a link into the description so you can see how a system of simultaneous equations can be extended to prove these results. Anyhow, so now we've got the raw ingredients, let's have a look at how a certain question could have looked, hypothetically, in an alternate universe, which included it on its specification for A-level. So let's imagine this question coming up in your A-level exams. It might word something like this: by analytically considering the total area of increasingly thin strips, each of which delta x, between the curve y equals x cubed, x equals a, x equals b, and the x-axis, prove from first principles that the area bounded by those 4 lines, f of x, x equal to a, x equal to b, and y being equal to 0, which is the x-axis, is one and the same as the limit of the areas of those strips added together as the width of them shrinks down to 0, and then to show that that is also the same as the integral of x cubed with respect to x. We know what that is. I mean, we just add 1 to the power, then divide by the new power, and put in the limits b and a. So it's just about piecing it together and illustrating it clearly and robustly. What I would suggest we do is we actually just get a graph to visualize what's going on. So this is a graph of y equals x cubed. The red line is y equals x cubed. And here are these bars, each of width delta x. So I'm going to put in the limits a and b, and imagine I want to find the area in between the red curve, x equals a, x equals b, and the x-axis. As you can see, taking the rightmost limits, this curve is actually going to be over approximated by the area of these bars, because these bars pop out at the higher end. So these bits here, which are roughly look triangular, are going to form an overestimate. These are residues which we don't need. We'll approach that problem later. So now we've considered this setup. These dots here just illustrate like an uncountable amount of extra bars in between. So the first bar, second bar, third bar, and so on. So that's width delta x, and that's the nth strip, strip n. So strip 1, strip 2, 3, 4, 5. The 6th strip I've shown, the nth strip is there. So over here, these dots are going to represent essentially the other n minus 6 strips. So we can now see that delta x must be b minus a over n. Between a and b, we have n strips, and between a and b, that's a gap of b minus a. So essentially what I've said here is if I take n strips and multiply by the width of each, dx, that gives the total distance in between a and b, which of course is b minus a. And all I've done there is divided by n to get that result. So, moving forward, think about the first strip. The height would be a plus delta x, because taking the height at the rightmost point. If that's a, this would be a plus delta x. So because it's y equals x cubed, this one here, we take the value of a plus delta x and then cube it. So if I had done that height here, that height would be a plus dx cubed. For the second bar, the height we're taking it at is a plus delta x plus another delta x. This value here is a plus 2 lots of delta x. So for strip 2, the height would be a plus 2 delta x all cubed, which you can add on now. In the same way, for strip 3, the height would be a plus 3 lots of delta x all cubed, and so on until we get to the nth strip. And in the nth strip, I'm going to use this expression for delta x specifically, so we can see what the result actually comes out to be. For the nth strip, strip n, the last one, the height will be a plus n lots of delta x cubed. So if I sub delta x, in place of delta x, I mean to say b minus a over n, you can see here the n's would cancel at the top and the bottom. Oops, didn't mean to use that line. Hit there and there. So I'd get a plus b minus a, then the a's would cancel, just leaving me with b cubed. So therefore that's just showing that the last strip does go all the way to b cubed for its height. So that's just a final height added on. So now what we need to realise is the following. The total area of all these strips, this is sigma notation, which just means we're going to sum them all together. It's the sum from k being 1 up to n. This is the first strip where k is 1. This is the second strip where k is 2. It's a sum of f of x, wherever x may be, given by this expression. K is varying as k goes up, multiplied by delta x, which I've written as b minus a. So delta x is just for width. So all it's saying here is the total area of all the strips is the total area of their width times their heights. It's just the total area of the rectangles. However, because we're summing things together, and most of these are things in the summation are constants, a is a constant, b is a constant, and I've just picked n generic strips. B, a, and n are all constants. And what we're allowed to do is we can take those outside of the sigma notation in the very same way as we're allowed to move constants to the outside of the integral. So if I just put b minus a over n in brackets and imagine it's shifting to the outside over here, then I can rewrite this line as the sum of all the strips is b minus a over n multiplied by the sum from k being 1 all the way up to k being n, f of the different values of x summed up. But f of x, of course, is x cubed. So I can add in there that f of all of this just means the input cubed, because f of x is to cube the input. So now, and we've got this thing here in brackets cubed. So already it's looking awkward. It's only going to get worse. We can use a binomial expansion write this bracket out 3 times to expand it. I'm not going to show you how to do it, the video would be far too long. But if you were to take these two terms in the brackets, the a and the b minus a all over n multiplied by k, and expand it out, what you would get is 4 different terms. The b minus a over n I've left in brackets as a constant, and I've just expanded this bit here. So all I've really done is taken this to the power 3 and wrote it out in this form. So as you can see, there are 4 different terms, which I'm going to highlight now in different colours. So, these 4 different terms, because these are just one added to the other, these can be split across 4 different summations. So I'm just going to partition this sigma into 4 separate blocks, like so. So because b minus a over n is a constant factor for each, that also appears for each as well. So the blue part becomes this section here, the green, we get this body, the red goes here, and finally the purple. Now going back to before, when I said that the constants could be taken to the outside of the sigma, a cubed is again just a constant, so I can imagine this being one lot of a cubed, but the actual a cubed itself I can imagine just being moved to the outside and multiplying the b minus a over n, and just leaving their sigma of 1 from k being 1 up to n, which we saw from before, will just give us n. And so this one here will just become b minus a all over n multiplied by n a cubed. I'll leave the other ones until a bit later, but for now I'm just replacing this, as I say, with b minus a over n, and this becomes n a cubed, because a cubed is just a constant. What I've done with the others is the other bits which are constants with these, I've just moved to the outside too. So for this one, from k being down to 1 up to n, I've just moved the 3a squared b minus a over n to the outside, because all that will be a constant. Similar over here, I've moved everything apart from the k, which is varying from being 1 up to n. All of this we can move to the outside, like so, to give us that. And similarly over here, for b minus a all cubed over n cubed is all constant, move it to the outside, expand this bracket and simplify, we get that. B minus a times b minus a cubed gives b minus a to the power 4. So again, I'm missing many working steps, just showing you the summary, but even as you can see, the summary itself is very unwieldy and hard to look at even. It's just a mess. So we're making progress, however, at least. So what we've got now are 3 different sums to do. The sum here of the first n natural numbers. Over here we've got the sum of the first n square numbers. And over here we've got the sum of the first n cubed numbers. This is where we're going to use the results I mentioned before, the power sum results. So we can actually evaluate these in terms of k. So what we're going to have next is this. So the sum of the first n natural numbers is a half, whoops, wrong colour, half n squared plus n, from that result we mentioned before. The sum of the first n squared numbers is that, and the result for the sum of the first n cubed numbers is this here. Now what we need to do is expand out and then neaten up, and pause the video at any point and try this yourself. The next line, what we're going to get when we expand up out all these terms, we'd get something like this. So again, hoping the colour coding helps with the lines. I've left the blue as it is. The green, this fraction times that, gives us these 2 separate fractions. The red becomes that, because we've got 3 terms here multiplying it by. So 1, 2, 3. And similarly for the purple line. If we have a look at what we've got now, we've got different denominators. These have no denominators, of course. And some of the denominators are constants. We've got quarters and halves. But some denominators have n's within them. So I'm just going to rewrite the order of this horrid expression here and put anything without n in the denominator first, and anything involving an n in the denominator last. So reordering this line, I can write it like this. So I'm just leaving anything to do with n on the denominator being last. Or the first part here, we can see the denominator is not affected by n. So, as n obviously approaches infinity, the stuff I've just written at the end, where n is the denominator, wrong colour, all of this will tend to 0, because if n is on the denominator and it tends towards infinity, if we're dividing by a value which is getting bigger and bigger and bigger, the actual value itself will become smaller and smaller and smaller after that division. So this will shrink down to something minuscule, and in the limit will be tending to 0. Also, as n goes towards infinity, as the number of strips becomes infinite, or goes towards a large value, the total area of all those strips will tend towards being the exact area under the curve. So if you picture this illustration here of y equals x cubed, and imagine it going from 2 to 4 to 8 to 16 to 32 and so on strips, you can actually visually see the error, the bit above the bars, the bit of the bar, sorry, which is over the line, the proportion of the bars over the curve tends to 0. And as you can see, as the bars become more and more numerous, the approximation becomes more or less perfect. So using that concept and this idea, we can therefore deduce that the area under the curve, from x being equal to a to x being equal to b, is given by this expression here, because everything in yellow will just shrink down to nothingness, leaving us just with this here, because all the rest of it has become negligible. This itself, we need to expand out. So if I were to expand out all of these terms, I get this horrible looking result. And if you have a look now, we've got different types of terms which can then be grouped together. So I've got some terms involving a cubed b. If I were to ring those, this is to help you. So I've got a cubed b over here. That's a b cubed a. That's a cubed b, and so on. I've got a to the power 4. Different terms. In fact, you can do the rest. It's a slog. It's also easy to make mistakes when simplifying these very long expressions, because, for example, I'm very tempted to confuse a cubed b with a b cubed. So you need to be very careful when simplifying it. So have a go. What you should find is it simplifies down perfectly to 1/4 b to the power 4 minus 1/4 a to the 4. Now that result should hopefully resonate with you if we're integrating x cubed in between a and b. So, obviously we know if we just take the integral from b down to a of x cubed dx, that's one and the same thing. So, integrating x cubed dx between b and a, we know we'd get 1/4 b to the power 4 minus 1/4 a to the 4. But after all of this horrid algebra and summations above, we've realised that by taking ever increasingly thin strips, the area underneath the curve on the x-axis also becomes one and the same. So therefore, 1/4 b to the power 4 minus 1/4 a to the 4 must be one and the same as the limit, as those widths shrink down to being 0, of all the strips in between a and b added together with width dx and height x cubed. So I've got a sandwich essentially, one thing at the start, the integral, equal to the exact numerical result, equal to this summation. So if we've got a equals b equals c, a equals c. And we can read it the other way around. In other words, the limit as delta x approaches 0 of the summation of all these infinitesimally smaller areas tends to the exact integral x cubed dx in between those exact limits of integration, which proves very nicely and robustly the link in between numerical algebraic integration and what it actually represents in terms of geometric areas underneath shapes. Taking it slightly further though, that was just for y equals x cubed. So yeah, just putting a piece of that result together like I just doodled over. So in the case of y equals x cubed, we've got our result pretty watertight. However, what if for just a general function y equals f of x? So generally for any bounded function, with y equals f of x being continuous and positive in between a and b, just to make it simpler, we have that the area bounded by y equals f of x equals a, x equals b, and y being equal to 0 is the same as the limit as delta x approaches 0 in between a and b, x cubed delta x, which is the integral x cubed dx. So now we've proven it. Thank you very much for getting through all that. That was not, I don't think, straightforward. If any of that has made sense to you, thank you for staying with it. I must stress you don't technically need to know this for your A-level mathematics exams, but I would have appreciated it myself if I'd have known why integration works with some sort of tangible examples, rather than it just being presented to me in a way where I had to assume it was true. I can understand why my very good teachers didn't go into depth with that, but if you were like me and wondered why it works, and you wanted a more visual representation, hopefully that's served a purpose. So from me, as I'll say again, thank you for listening, and I hope to see you very soon. So for me, it's goodbye from me.